Welcome to part 3 of our webcast series on Oracle Database in Memory. In this session, we're going to focus on how the in-memory column store is kept transactionally consistent with the rest of the database during data load activities. Data loading or DML operations come in 3 forms. Your standard conventional insert or update statement, which typically affects just a single record. Then there's the direct path or bulk load operations, where we're going to insert a large volume of data, typically above the high watermark of an object. And of course, partition exchange loads if you happen to have a partitioned table. Regardless of which approach you take to insert new data into the Oracle database or update existing data, we're going to be able to keep the in-memory column store transactionally consistent at all times. Now, I'll explain in detail as we go through the presentation how we're able to do that, but for now you can just think about it as how Oracle has always kept an index transactionally consistent with a table. So let's start by looking at a conventional DML operation. And by conventional DML, I mean things like an insert statement or an update statement. In fact, let's focus on the update because that's probably a little bit more interesting than an insert. Now, traditionally, when you do an update in the Oracle database, the first thing that happens is that the block that contains that row is read into the buffer cache. And a copy of the block as it exists now is also stored. You go ahead and you update the row, so a new copy of the block is created with the new changed row in it. And if you commit that transaction, then that change is recorded in the online redo logs by the log writer. And the new version of the block is written out to disk via the database writer. So what happens if you add in-memory or the in-memory column store to this situation? Well, if you recall from part 1 of our web series, the in-memory column store is a new pool of memory inside in the SGA. Now that pool is divided into 2 different areas, the IMCUs and the SMUs. So the IMCUs, remember, they're the in-memory compression units. They hold the actual data from the tables that have been populated into memory. The SMU pool, on the other hand, stores snapshot metadata units or information about what's going on with the data that's stored in the column format. So if we drill into it, what we'll actually see is that each table is broken up into multiple IMCUs. Each IMCU contains the column entries for a subset of rows within that table. Each IMCU has a corresponding SMU, and within that SMU, you'll actually find something that we call a transaction journal. And that's used to keep the column store transactionally consistent during DML operations. So how does it work? Let's imagine we want to update one of the rows that exists in this IMCU. When that update is processed, it will still go through the buffer cache just as it did before, and it will be persisted on disk via the redo logs and the database writer out to the database files just as it used to be. But what we'll find is as the DML operation is being processed in the row store, the corresponding entry in the in-memory column store is going to be marked stale as of the SCN of that transaction, of that update. And a corresponding entry will be written into the journal that's going to contain the row ID for the changed row. Now, the reason we don't instantly update the entry in the in-memory column store is that the column store, remember, is being used for analytic queries that can often be a couple of seconds long, and perhaps there's an ongoing analytic query running that's going to need to see the old version of that row. Because remember, Oracle always offers transaction consistency, so you'll see the data as of the SCN that is for your transaction. So if a transaction was running before this update happened, it'll have an older SCN than the update, and so it's going to want to see the original version of the entry in the column store. Remember, the in-memory column store is never out of date. In order to achieve a read-consistent image of all of the data for a query that comes in after the update, what we'll do is we'll scan the necessary columns from the IMCU. We'll find that there is one entry that's stale as of an SCN that's older than our query. And what that will do is trigger us to go to the journal and merge the results that we get from there by looking up that row ID in the buffer cache to get the newer version of that row. As you can imagine, as the number of entries in the transaction journal increases, then there is the potential to slow down the scan or analytic query performance because we're having to scan all of the entries in the IMCU and then pick up any of the entries that are stale from the buffer cache. So when the number of entries in the transaction journal hits an internal threshold, that IMCU is going to be automatically refreshed. Now, it's not the entire object, it's just the subset of rows from that object that reside in this IMCU. Now, this operation is online, and therefore there's no impact to the analytic query performance because it's always going to be available. It also doesn't block any DML operations on that object either because the IMCU is always available. So how exactly does it work? It works by taking advantage of something called double buffering. Let's imagine we've got an IMCU that has hit that internal threshold and is ready to be refreshed. The first thing we're going to do is we're going to mark the entire IMCU stale as of a given SCN. Now, it's still online, it's still available for queries, but it is going to be marked stale as of a given SCN. In the meantime, we're going to create a new version of the IMCU. You can consider this operation pretty similar to doing a create table as select, because we're going to grab all of the clean entries that are already formatted from the existing IMCU, and we're going to combine them with the latest version of the changed rows or the stale rows from that IMCU. And all the way through doing this creation of the new IMCU, we are tracking any DML operations that occur so that we can keep the new version of the IMCU completely up to date. And for a short time, both of the copies of the IMCU is going to be there in memory. We'll keep the older version around because there may be, as I said, older or longer running analytic queries that haven't read this IMCU but will need to. So we do keep the original around for a little bit. The new version is also there, marked with the new SCN, so that depending on when your query begins, it will read the appropriate IMCU. Now, those older IMCUs will just automatically get aged out, either when we believe there are no more transactions that need it, or if we're under a very tight space constraint. But because this is being done on a per IMCU basis and not on a table or even a partition level, the amount of additional memory that we're using in order to do this operation is actually quite small. There are actually other cases where an IMCU may be automatically refreshed for you, even if we haven't hit that internal threshold to refresh the IMCU. We call this behavior trickle repopulation. And what's going to happen is the IMCU background process is going to wake up every 2 minutes and check to see if any of the IMCUs have stale entries. If we find an IMCU with some stale entries, what we're going to do is we're going to create a new version of that IMCU, just as we did before, by combining the clean entries from the existing one with the latest version of those changed rows. And again, the original IMCU will be marked stale as of the SCN that we're going to use for this operation. And it will still stay online in the in-memory column store for any longer running transactions or queries that may be going on that may need it. But in the background, we're going to rebuild and create a new version of that IMCU. And again, we'll be tracking any of the DML operations that occur during that creation time. They'll be journaled to ensure that the new version of the IMCU is completely up to date. So either we'll hit that internal threshold and rebuild the IMCU for you, or trickle repopulate will kick in every 2 minutes and just refresh any of the IMCUs that might be dirty. So there's a couple of things that are going to determine the repopulation performance in the in-memory column store. Obviously, the rate of change, so how quickly the data is changing within your tables, will determine the repopulation performance, how often it's going to occur. In terms of system resources needed to do the repopulation, that's going to be influenced more on things like the compression level that's been chosen. Tables with a higher compression level will incur more overhead because those compression levels are quite CPU intensive and therefore will require more CPU to maintain or rebuild the new version of the IMCU. The location of the changed records will also impact your repopulation performance. If all of the changes are co-located in the table, in other words, they occur in a small subset of rows, and those rows are all in the same IMCU, then what's going to happen is that we'll have a less impact because all of those changes will be able to be done with the refresh of a single IMCU. On the other hand, if you're changing rows that are dispersed throughout the entire object, so a small number of rows would change in all of the IMCUs that make up that object, then that will also have an impact on the repopulation performance because the number of IMCUs that would need to be changed would be far greater. And of course, inserts are going to be much cheaper than updates. Inserts just are new entries going into an existing IMCU, so pretty straightforward, where an update, as you saw, requires us to be able to keep an older copy of the data around for a little bit of time so that older operations can take advantage of the in-memory column store. The other thing that greatly influences the performance, of course, is the number of worker processes that are able to complete this repopulation work. And you can control the number of active worker processes using the initialization parameter in-memory repopulate servers. And in-memory trickle repopulate servers %. So that's the percentage of worker processes or repopulate servers that you are willing to allow the system to use to do trickle repopulations. Now, if you don't want us to do trickle repopulations at all, you don't want the IMCO to wake up every 2 minutes and check if there's anybody who needs to be refreshed, you can simply set in-memory trickle repopulate servers % to be 0. So what you'll find is that an insert or update statement will be processed in the Oracle database just as it is today. It'll be processed through the buffer cache, but those changes will be instantly reflected in the in-memory column store and IMCO and the worker processes that are going to refresh any IMCU that's been impacted by those DML operations. So let's move on and look at our second type of data loading operations. And in this case, we're going to look at direct path data loads. A direct path or bulk data load operation is typically done when somebody does a create table as select command or an insert with an append hint. In these cases, what we're looking at is actually putting a large volume of data into the database within a single operation. So let's take a look at what happens when somebody does this. Let's imagine we have a sales table that's already populated into the in-memory column store, and then somebody does an insert append operation to add a large number of additional rows to our sales table. When a direct path operation occurs, it's going to be an all or nothing operation. In other words, since we're putting so much new data into an object, we either want that load operation to fully succeed, in other words, you see everything, or we want it to fail completely and have nothing. So if something goes wrong, we don't want you to see any of the rows at all that were involved in this operation. And Oracle's able to do that by inserting the new data above the high water mark in the table. Now, if you're not familiar with an Oracle high water mark, what it is an indication within that object where the last row resides. So as soon as the database that's scanning that object hits that high water mark, it knows that's the end of the table. Even though there might be additional space left in that database block or even in that database extent that you're reading, as soon as you hit the high water mark, that's the indication to the reader process that you're done. You've got all of the data from this table. So with direct path load operation, what's actually going to happen is the new data will be inserted into new database blocks that actually appear above the high water mark. That way, Any other process in the database that's having to read this object won't actually see those changes yet. What they'll do is they'll read the object, as I said, they'll hit the high water mark, and they'll think they're done. Even though new data is being inserted above that, they're not aware of it, because with a direct path operation, as we said, is all or nothing. Until the operation is committed, no other process in the database gets to see that new data. So from the in-memory column store point of view, it's not aware of that new data at all. It thinks it has all of the data for the sales table, as it rightly should. And so if you looked in $IM segment, even while the load operation is going on, the in-memory column store believes it's got all of the data. Once the direct path load operation has actually completed and the user has committed it, what's going to happen is the high watermark is going to move to encompass those new database blocks. They're going to become part of the object. And it is that moment on the commit that the rest of the database gets to find out that there is new data in that particular object. And as soon as the commit happens, the in-memory column store becomes aware of the fact that it's missing some of the data from the sales table. And if you were to query $IM segments, you'll notice that the bytes not populated column is going to suddenly indicate that it's missing data. Now, if the sales table has a priority on it, if you remember back to our previous sessions, we talked about the in-memory attribute actually having some subclauses, one of which is priority, which determines when an object is brought into the column store. So if our sales table has a priority specified on it, then the data will be automatically populated into the in-memory column store as soon as it's been committed. In other words, as soon as we figure out that we're missing some data, we'll automatically bring it into the column store, assuming we've got capacity for it. However, if the sales table does not have a priority specified on it, which remember is the default, then the missing data won't be populated into the in-memory column store until somebody accesses it for the first time after the commit. As soon as they access it, we'll begin the population, because we have been then told by the end user effectively that this is important data, that we need to have it in the in-memory column store because we're interested in querying it. So let's examine our third and final data loading operation, and that is, of course, a partition exchange load, and see how the in-memory column store is affected by these kind of loads. So let's now turn our attention to our third and final data loading operation, which is a partition exchange load. And let's see how the in-memory column store is going to be kept transactionally consistent during one of these loads. So before I actually talk about a partition exchange load, I wanted to spend just a few seconds talking about partitioning in general. So partitioning is a feature or functionality offered in the Oracle database that allows you to take a large table and divide it into multiple smaller objects called partitions, which in turn can be divided into, again, even smaller objects called subpartitions. The goal of partitioning is to improve query performance by accessing only the pieces of the table that we need to answer the query, but still allowing you to manage all of that data as a whole as a single table. So although it's been broken up into individual pieces, from the database perspective, it's still logically a single table. So you can make changes to that. That will affect all of the partitions, so it makes management easier. But from a query perspective, we're able to prune down or access only the partitions that we need for the query. So twofold benefit from using partitioning. Given that each of the partitions has its own physical properties, you can actually have the partitions reside on different levels within the Oracle database. So for example, they'll all of course reside on disk where they're stored, but that disk may be traditional spinning disks, it may be SSD, it may even be flash. And because they've got their own separate physical attributes, a subset of them could appear in the in-memory column store. As I said, the primary benefit of partitioning is to increase query performance. And it does that by dramatically reducing the amount of data that needs to be accessed in order to answer a query. Because what we're able to do is just go after the partitions that are needed for that particular query. All of the other partitions in the table are simply ignored or not read. And of course, because each of the partitions has its own physical attributes, then each of the partitions can have a different in-memory attribute specified on it. So you can have partitions from the same table in memory at different compression levels, or you can have a subset of the partitions in memory while the rest of the table is not. That way, you can bring just the data you need from the table into memory and not waste the valuable memory resource on data that's not necessary for your existing query workload. So let's now talk about partition exchange loads. The ability to load data into a partition table by simply exchanging an existing empty or partially populated partition with a new table or copy of the data that you wish to have in there. So how does this work? Well, let's imagine we've got a set of data files that have shown up that we want to get loaded into our partition table. The first thing we're going to do is create an external table for those flat files that have arrived. Now, an external table, if you're not familiar with it, allows us to basically access flat files or data in flat files as if they were a table in the Oracle database. Once you've got that external table created, you're going to do a create table as select from the external table, and it's going to create a non-partitioned table that holds all of the data in the flat files inside in the Oracle database. Now, if you needed to transform that data in any way in order to ensure that it reflects the same format as the table, that would be done, that transformation would be done as part of that ctas command. So now what we have in the Oracle database is a table called temp sales that has all the same columns and formats as our sales table, but it's non-partitioned. And since we're doing this in Oracle Database 12c, that temp sales table will automatically have optimizer statistics gathered for it as part of its creation, as all create table as select operations now automatically gather statistics. Because each of the partitions is its own physical object and therefore has its own physical attributes, we need to ensure that the temp sales table has the physical attributes that we want for our partition after the exchange. And since we want the partition to be in memory, we're going to go ahead and set the in-memory attributes for temp sales, and we'll actually populate it into the in-memory column store before we do the exchange. Now, the reason we do that is to ensure that immediately after the exchange occurs, anybody that queries the sales table will get this latest information directly from the in-memory column store. Because remember, during a partition exchange load, no data actually moves, it's all metadata that changes. So now that we're ready, we're going to do the alter table sales exchange partition to bring the new data that we've just loaded into temp sales and swap it for the empty partition we had in the sales table. Now, as I said, no data is going to move. What actually happens is that the partition table appears in the data dictionary as a linked list, and we simply break the link between the May 23rd partition and the May 24th partition, and we make that link now point to temp sales. So the new partition or the new data is seen as the May 24th partition, and it's going to pick up all of the physical attributes that the original temp sales table had. So that means it will be in memory, and we'll be able to query it directly from the in-memory column store. So what will be in temp sales? Temp sales will now appear empty, just as the May 24th partition was empty. So what did we learn in today's session? Well, the in-memory column store is going to be fully supported with all of the data loading mechanisms that Oracle supports, whether it's a conventional insert or update statement, whether it's a direct path load operation or bulk load operation, or a partition exchange. Either way, the in-memory column store is always going to be kept transactionally consistent with the rest of the database. The presence of the in-memory column store does not impact how the data changes are persisted on disk. If it's a direct path load operation, or if it's a partition exchange, or if it's a conventional insert or update, all of those changes are persisted to disk just as they are today, and there's no increase in the amount of redo or undo that would be generated for these operations, because the in-memory column store only resides in memory and is not persisted to disk. We actually don't do any redo or undo in order to keep it in sync. If the database should crash, we'll simply rebuild the in-memory column store from the row format that is persisted on disk. So there's no additional redo or undo generated to keep the column store in sync. If you want more information about Oracle Database in Memory, please take a look at the in-memory blog, which you'll be able to find on blogs.oracle.com/inmemory, or take a look at some of the other videos we have on our YouTube channel, or the white paper is another great resource to get more information.